Hello everyone, welcome to my channel. Myself Vignesh Anand. In this video, we are going to see the types of thyristors. Actually, in first part, we have seen up to the four types of thyristor. From fifth reverse conducting thyristor, we are going to see in this video. So coming up to reverse conducting thyristor. So normally, the thyristor in the sense it converts the AC to DC. So the thyristor usually allows a current in a forward direction while blocks the reverse direction current. However, an RCT consists of a SCR integrated with a reverse diode, which eliminates a undesired loop inductance and reduces a reverse voltage transient. So the freewheeling diode or the reverse conducting diode, which is placed in parallel with the RCT circuits. So whenever there is a turn off and also the improvement of commutation also been taken place by the freewheeling diodes, and also it helps in uh, providing a protection for against the reverse voltage transients. So it has a low reverse voltage rating than its forward voltage rating. Because of the reverse current flow, it allows the RCT to drain its carrier from its junction relatively faster than the fast speed switching speeds. Then its application, it is mainly used in your DC drives for traction applications and also for high power choppers and inverters. So this is your circuit. In here, with the normal thyristor, additionally we have a freewheeling diode. Then gate turn off thyristor. This is one of the main term used in work conversions. So it consists of a anode, cathode and gate like a normal conventional thyristor. This divide is used to turn on and turn off the main circuit supply through a gate drive circuits. So it is to activate the GTO into the mode of conduction. A small positive gate current or a voltage is required, and when giving a negative pulse on the gate terminal, and it is capable of being switched off. So this GTO is divided into two types. One is your symmetrical GTO and another one is your asymmetrical GTO. So normally the normal thyristor, in the sense the turning off condition is not possible, so manual commutation need to be done. But in the case of GTO, the turning off also can be done. But one thing is that during the turning off, it requires a high power of currents. So the symmetrical GTO that capable of identical forward and reverse blocking, which are applicable in current source inverters. However, these are fairly slow. It has a high reverse blocking capacities also. Next is your asymmetric GTO. This is mostly applicable because of their low on-state voltage drop as well as a constant temperature characteristics. So it has a small reverse blocking capacity as 20 to 30 volts. Next is the application working. In forward blocking condition, the voltage is applied across the thyristor without applying the positive gate signal. Therefore, it does not conduct in this mode. But there is a little leakage current which is very high, which means very much high when compared to the thyristor leakage current. And also when a positive gate signal is given with appropriate altitude to the GTO, then it moves to the forward conduction mode. So whenever a reverse voltage is given to the thyristor, it blocks, and the reverse voltage is blocking will be up to certain limits only. So whenever the avalanche breakdown takes place, then automatically the GTO starts conducting in the reverse direction. So this mode of operation does not destroy the device if the gate is negatively biased and the time of the operation is very much smaller. Then coming up to the advantage, the GTO has a outstanding switching characteristics. The configuration of the GTO circuit is very less weight and also the size is compact. Then it does not require high cost weight and uh, the switching operation of the GTO is higher as compared with the SCRs thyristors. Then the blocking voltage capacity of the GTO is high, and also the di by dt ratio is more at turn on. Then coming up to the disadvantages, on state voltage drop is high. Then the structure of the GTO is multi-layered, so the gate triggering current value is high as compared to the conventional transformers thyristors. High loss of gate drive circuits. Then the latching and the holding current magnitude is high as compared with the SCRs. Then the triggering current of the GTO is very much higher than the SCR. So it is commonly used in your chopper inverters and main circuits, then AC drives and DC drives, then low power applications, then for the AC stabilizing power supplies, then also it is used in your industrial areas as a rolling mills and machine tools, and also for the robotics. So these are all the main applications used for in the GTO. Nowadays, the GTO is further upgraded as a MOSFET type of turning off, then emitter type of turning off also. This is your common symbols of your GTO circuit. Next is your MOSFET turn off thyristor. It is a high power bipolar MOSFET thyristor that constitute both MOSFET and the gate turn off thyristors. So it is a combination of MOSFET and gate turn off thyristor. It consists of anode, cathode, and then gate 1 and gate 2 terminals. So the GTO can only go into a off state when a high pulse of current is provided, but in case of MTO, the combination of MOSFET and GTO together allows it in even a very low pulse of your current. So it is very much compactable and also very much easier for handling, because the switching off and switching on characteristics itself, if you compare with the GTO, it is very much upgraded. These MTOs are then working two gate terminals, which are the gate 1 and gate 2. Gate 1 is for your turn on and gate 2 is for your turn off. It is has a ideally bistable switching behavior and low power dissipation in both turn on and turn off states. So to switch on the MTO, a current pulse is applied on the gate 1, which latches the devices by switching the NPN transistors on. Then the collector current then provides a base current to the lower PNP, which provides in a switching the PNP transistors on, which latches the MTOs. Then to turn off them, a gate voltage is applied at the MOSFET gate, which means your gate 2 terminal. This turn on the MOSFET, hence shorting the emitter and base of the MTO, which stops the latching processes. So the main advantage of the MTO is it has a high power rating range from 10 kV to 4 kV, 10 kV and 4 kA, and it requires a small snubber circuit, which means the snubber circuit is used in your protection of against your high voltage transients. So for in this case, the snubber circuit requirement is very much smaller. Then the cost of your component and gate drives power requirement is very much lower than the other turn off devices. Coming up to the applications, it is normally used in your UPS systems. Then for the medium voltage motor drives, ship propulsions, then for your large motors and fans, then for reactive harmonic compensators, for a high power converter applications such as your FACT, which means your flexible AC line transmissions, due to the low current gate drivers. And also requirement of your small snubber circuit also makes the devices into a compact level. Then it is a high power level of switching because it require very low current for current or voltage for switching on and off. So in this case, the accuracy of MTO is very much higher than the GTO or normal thyristors. This is your MTO symbols, which is consist of anode, cathode, and gate 1 and gate 2. So normally the turn on and turn off gates are provided at the top and the bottom. Then the anode and the cathode at the other end. So it is a combination of your MOSFET and GTO commonly. Then equivalent circuit. In equivalent circuit, you will keep a transistor in the opposite end of your, which means parallelly to the GTOs. Sorry, MTOs. Next is your emitter turn off thyristors. So ETO, it is also used in also a combination of your GTO and MOSFET combinations. So it consists of a two N MOSFET and P MOSFET and also a gate. So an N MOSFET is connected in a series with the cathode terminal and the P MOSFET is connected between the gate and the cathode terminal of your SCRs. Coming up to the working of your ETOs, it has a two gate terminal, a normal gate terminal for turning on and another gate terminal for your turn off with a series N MOSFETs. It turns on by applying a positive gate voltage to the both gate, making a NMOS turn off and a PMOS for your turn off. So it turn off by applying a negative voltage to NMOS gate, providing the residual carrier to the flow out through the PMOS, which also provides a fast switching. Next is the application. The ETOs are commonly used in your voltage source inverters for a high power, then for a flexible AC line transmissions, and also for the static synchronous compensators. Next, we will see the basic diagram of your ETO. So it is your symbol or connection diagram of your ETO. It consists of anode, cathode, then the two MOSFETs, N and P type MOSFETs, where the N type is connected in series with the cathode and the gate terminals, and the P type is connected in series with the gate and the cathode. Just for understanding, I have splitted that's depletion layer, P and N type layers. So in here we have two gates, as I said. P and N type MOSFETs are used between those gates. So for turning on and turning off with that gate pulse, we will turn on and turn off the thyristors. Isn't all the basics of your types of thyristors? In coming up video, we will see the explanation one by one separately. Hope you have understand the thing. So see you in next videos. Have a nice day. Nandri, vanakkam.